For example 1, I'd like to solve the linear equation 2x minus 5 is equal to negative 1 half x plus 5. What this means graphically is where do your two equations intersect, which is right here. So I'm going to label that point. I can actually see that it happens at x is equal to 4 and it has a y value of 3. So what we'll do is match that up with the answer when we solve this. Just a couple of other things first. I have two different functions here, so we've been calling functions f. But if you're dealing with two functions at once, it might be nice to give the other function a different letter, so you could call it g. And that means 2x minus 5 is going to be f of x. Again, the slope is definitely positive and the y-intercept is negative 5. Therefore, my other function is g. It has a slope of negative 1/2, the line is decreasing, and the y-intercept is positive 5. So what we're doing graphically is solving where is f of x equal to g of x. And I know that the answer should be at 4, 3. But let's actually do this by hand, not using a graph. To do this, we'll set the two equations equal to each other and try to isolate x by itself. That is, group all the x's, put them on one side of the equation, take everything without an x and move it to the other side. So a good strategy for solving some type of linear equation that has fractions is to cancel all the fractions. Since I have a 2 here in the denominator, if I multiply both sides of this equation by 2, it'll cancel here. All that means is I'm going to multiply every single term by 2. So if I multiply 2x by 2, it doubles to give me 4x. If I multiply 5 by 2, I get 10. If I multiply this negative 1/2 by 2, 1/2 times 2 is just 1. You don't have to write it, and we're left with negative x. And lastly, if I multiply 5 by 2, I get 10, so that's plus 10. So just a good strategy if you have fractions. You can cancel them by multiplying by the least common denominator. Okay, so next, what I'm going to do is add this x to the other side of the equation. This gives us 5x minus 10 is equal to just 10. I'll now add 10 to both sides. So I get 5x is equal to 20. Okay, and when I divide both sides by 5 to get x by itself, I have my solution of x is equal to 4, which is perfect. Over here, the 4 was in fact the x value since it's on the x-axis. So that 3, that y value over here, that means if you were to take 4 and put it in place of these x's, you would get the y value for both f and g, and they would be exactly the same thing. In fact, they'd be 3. But when we solve an equation, the original equation only had x's in it. If you come down here and write x is equal to 4, that's a perfectly fine way to express your answer. So the point of this example is, anytime that you solve a linear equation, it's where the two graphs meet. So for example 2, all we're going to do is solve this linear equation, keeping in mind that what we are finding is the place where these two graphs meet, where they intersect each other. But you really don't need a graph when you're going through this process. It might be nice at some point to use that to check our answers, but all I'd like to do is just solve this without using a graph. So this example has decimals in every single term. You could just distribute the 0.3, the 0.4, and the negative 0.4. But another approach you could take is, if you multiply both sides of this equation by 10, it'll move the decimal one place here, here, and here, changing it from decimals to whole numbers. So let's actually do that. Not necessary, but you can definitely take this approach. So that is, if I multiply this side by 10, 10 times 0.3 would change to just 3. I now would multiply to this next term, and that changes the 0.4 to a 4. And on the right side of my equation, that negative 0.4 just becomes negative 4. So what we've done here is multiply both sides by 10. And when you do that, it takes each of the three terms, moves the decimal point on each of those values. Okay, so to solve this equation, what I'm going to do is distribute in the 3, distribute in the 4, as well as the negative 4, and go from there. So 3, if we multiply it into the parentheses, gives us 3 plus 3x. If I multiply the 4 into the parentheses, I get 8 plus 4x. And on the other side, if I distribute in the negative 4, I get negative 4 plus 12x. All right. You could start adding and subtracting things to one side of the equation or the other, but this side over here I have some like terms. I have a 3x and a 4x, as well as a 3 and an 8. I'm going to combine those into just two separate terms. 3 plus 8 is 11. And 3x plus 4x is 7x. That's equal to negative 4 plus 12x. All right, next, I think what I'll do is add 4 to this side, then subtract 7x to this side. Let's see what we get there. Okay, if I add 4 to both sides of my equation, I get 15 plus 7x is equal to 12x. If I then subtract 7x from both sides, I get 15 is equal to 5x. Here I can now divide by the number that's in front of the x, which is a 5, and that gives me my value, x is equal to 3, and that's my solution. We could at this point go back to the very original equation, take this 3, put it into all the x's just to check that the left side is equal to the right. You can try that if you'd like. Really what I wanted to go over here is a process for solving a more complicated linear equation. And for example 3, same idea, just solving a linear equation without using a graph, just using a couple of different techniques. So for this one, we have 3 separate denominators, and I think a good approach would be to cancel the denominators from this problem. And the very first example we did, it was really simple because there's just one fraction, so we multiplied both sides by 2. Here, we have a denominator of 2, 3, and 6. So instead, I'm going to use the least common denominator for those 3 fractions. Since the denominators are 2, 3, and 6, I can multiply to get to 6 in every single case. That's my least common denominator. What I'll do is multiply both sides by 6, meaning I'll put a 6 over 1 in the front of every single fraction. So here's what we have. 6 over 1 times our first fraction. Okay, then we have minus, now again I multiply by 6 over 1 on my second fraction. And on the other side of my equation, same thing. I'm just multiplying 6 over 1 to the fraction 2x minus 1 over 3. So I've multiplied both sides by 6. But in doing so, 6 cancels into this 6, leaving with just 1s. 2 goes into 6 3 times. And 3 goes into 6 twice. And we have to be just a little bit careful here. All the denominators are just 1. I don't have to write another denominator again. What I do have to watch out for is, technically this 3 is multiplied to both terms over here, so I'm just going to include some parentheses around these. Over here, there's a 1 in front of x plus 1, so you could put 1 with parentheses x plus 1. Ultimately, that won't make any difference in the problem, so I'm just going to write x plus 1 for this very first term here. So I mean, we have x plus 1 is being multiplied by 1, but I don't have to write that again. For the next term here, this is just 3 times x minus 3. So here I have to be careful. I'm going to put parentheses around the x minus 3. And I'm going to do the same thing to the other side of the equation. That 2 is being multiplied to 2x minus 1. So what we've done is change our first equation to one that has no fractions in it, And we have a really easy technique for solving this type of equation. I'm going to distribute in this, being careful here, this negative 3, as well as this positive 2. Working left to right, I have x plus 1. When I distribute in the negative 3, I get negative 3x plus 9. And that's equal to, okay, distributing in the 2 gives me 4x minus 2. Okay, again, I think I'll combine like terms on the left side of my equation. I have an x minus 3x, that is a negative 2x. And then I have a 1 and a 9. They're both positive, so that's a positive 10. And that still is equal to 4x minus 2. Great. I think now I'm going to add the 2x to this side, add the 2 to this side. If you'd like, you can even do this in one step. I think it's worth writing that down, but you can do this all at the same time. I just added 2x to both sides. At the same time, you can say, well, why not just add this 2 if you want to save yourself a step. What we have left over is, on the left, 12, and on the right, 6x. You could take 2 steps if you'd like, but I've done the same thing to both sides of my equation in this step. All right, I'll now divide both sides by 6, and that takes me to my answer of 2 for x. So that's the final answer. You could, again, take that value, plug it back into the original equation just to make sure the left side equals the right. But that is it for this example.